Hello everybody and welcome to the Physics channel video of 2017. I'm Rocket and this is the first episode of the year. It's, as I just said, it's the big questions made little. Now last time I said I was going to be starting a 2-year long series all about the elementary particles, with one episode focused on each one. We're doing 9 episodes a year. Problem with that I found was that means I'm going to have to find an episode's worth of information on each elementary particle. That ain't happening. There's all of them are so a lot of them are so similar. There are a lot of them that have similar or the exact same properties that I'd just be repeating the same information to you, and you just get really bored. Which I don't want to happen, obviously. So what I'm going to do instead is I'm going to be doing, over the next 6 weeks, starting today, with this episode, an episode focused on 3 elementary particles each. So this episode, as you have read on the title, is going to be entirely focused on the up quark, the charm quark, and the top quark. Yeah, I kept trying to say the wrong words there. Yeah, the up, charm, and top quark. A lot of them have similar or the same properties, but I'm going to get right into it. So I'm going to start off with the up quark. You are roughly half of your mass is up quarks. In one of my last videos, I said that we're all made of atoms. That's what we're all made of, and atoms are made of 3 types of particle: electrons, protons, and neutrons. Now, protons and neutrons, electrons are elementary particles in their own. I'm going to talk about them in future videos, but protons and neutrons are made up of up and down quarks. In general, atoms tend to contain slightly more neutrons than protons. Not always, but usually they tend to contain slightly more. And because an up quark contains, a proton contains 2 up quarks and 1 down quark, and a neutron contains only 1 up quark and 2 down quarks, there tend to be slightly more down quarks in your body than there are up quarks, but roughly half or a bit less than half of your body mass is made up of up quarks, which is pretty cool. Now they all have all up quarks have an electronic charge of plus 2/3. That's their electric charge, and they have a mass of 1/3. And the unit for the mass is, if you had 1 mole of a substance, so 6.022 times 10 to the 23 particles, or that massive number appearing on your screen right now, the mass you have would be the grams given in, so the number given in grams. So the unit for mass is grams per mole, or grams per 6.022 times 10 to the power 23 particles. That number, by the way, is called Avogadro's number, and it's used a lot in chemistry. But that's the mass unit we use. So an up quark has a mass of 1/3 grams for every 6.022 times 10 to the power 23 up quarks there are. Which, considering how many up quarks that would be, and how little that mass is, they're really small. They're really light. All elementary particles are small and light and everything. Yeah, so I'm now going to move on to a top quark. That also has a charge of positive 2/3 electric charge. It's called positive 2/3 e, and actually a charm quark also has positive 2/3 e electric charge. Going back to the top quark, it is the heaviest elementary particle. It has the highest mass of all the elementary particles. The mass of 1 top quark is about the same as 1 atom of tungsten. So 1 atom of tungsten has a mass of 183.84 roughly. So it's about 184 grams per mole, which compared to the Up Quarks, which I just mentioned, is quite a lot. Obviously, all elementary particles have an antiparticle, are exactly the same as a matter particle, but all the charges of everything are negative. So when you have an electrical charge of something, in this case, if we talk about top quarks, it's plus 2/3 electric charge. A top antiquark, or an anti-top quark, or anti-top, it's all kinds of words you could use to describe it, would have an electric charge of negative 2/3. However, the mass is still the same for all of them. There's this other thing called color charge, which can change and vary with different particles. However, if you combined a up quark and a top quark and a top antiquark, or an anti-top quark, or an anti-top, whatever you want to call it, they would have to have equal and opposite color charges. So the top quark would have to have a red or a blue or a green charge, and obviously this is the only color charges you can have. And the anti-top quark would have to have the anti-red, anti-blue, or anti-green charge, respectively. One having to pair with the other in the order I said them. This applies to all elementary particles. I'm just using the top quark as an example here. Well, all elementary fermions. I'm about to explain what a fermion is, but I'm moving on to the charm quark now, which also has the exact same electric charge as the two quarks I've mentioned so far, the up quark and the top quark. And there's another thing involved called a spin. And all of these particles I've said so far have half spin. Now, quarks are these things called fermions, which is essentially matter particles. Fermion, the difference between a fermion and a boson is fermions have half integer spin, so half spin, and bosons have integer spin, so spin would be mentioned as being, say, 1. Another difference is that fermions have mass. They're considered to be matter particles, whereas bosons are energy or wavefront particles. They are force carriers, and they carry the 4 fundamental forces, but I'll talk more about those in future. I'm now going to talk a little bit about which fundamental forces apply to all of these different particles. So actually, all 4 fundamental forces apply to the up quark, the top quark, and the charm quark. The 4 fundamental forces are the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity, or the gravitational attraction force. I'll talk about those a bit more in the future, especially when I come to the particles that carry them. But the last thing I'm going to say about these particles is what they decay to. A top quark has a 99.8% chance of decaying into a bottom quark, a 0.17% chance of decaying into a strange quark, and a 0.007, which is really fun to say, percent chance of decaying into a down quark. When I say decay, it doesn't just randomly change. You've got to remember there's got to be a conservation of charge going on here, which means that if you added together all the charge on one side of the decay and on the other, they'd have to be equal. You can't have charge randomly appearing out of anywhere. So things like electrons or positrons have to be produced or uptaken during a decay reaction in order to preserve the charge, because electrons have, of course, a negative 1 charge. Positrons, the antimatter particle of the electron, has a positive 1 charge, hence the name positron, also known as anti-electrons, but I'll get to those a bit more in the future. With the charm quark, there is a 95% chance of it decaying into a strange quark, and a 5% chance of it decaying into a down quark. Note, it will not decay into a bottom quark. And finally, the up quark can decay into a can is often stable, hence why it is used in a atom, because they're very stable. They tend not to decay unless the atom is incredibly unstable, in which case you get this thing called beta radiation, when an up quark decays into a down quark and produces a positron and an electron neutrino, and a beta particle can be produced. Or vice versa can happen. A down quark can produce an electron or a positron neutrino and become a stable up quark. But I'm going to talk more about all that kind of stuff in my next video next week, when I'm going to be talking all about the other quarks that go hand in hand with these. So the up quark, of course, goes balanced with the down quark. Charm quark goes balanced with the strange quark, and the top quark goes balanced with the bottom quark. We'll talk more about those all next week. So I hope to see you then, guys. It's been a pleasure talking to you all. Please like, subscribe, and share the videos with your friends, and I'll see you all next time. See ya. Bye.